Hello everyone, my name is Yang Qixing and today I will present my Computer 3115 course project. My topic is about exploratory data analysis and the visualization of NOx emissions in diluted hydrogen combustion. And my presentation's keywords is mechanism of validation, low NOx, and EDA and machine learning. And this is a table of contents. The first one is project background and analytic framework. And the second one, comparison and selection of chemical mechanisms. And the third one is the influence of parameter K on flow, temperature, and NOx. And the last one is rapid prediction model for NOx. Let's begin from the first one. First, I want to explain why I chose this topic. And as you know, hydrogen energy is very important for low carbon development. It does not produce carbon dioxide during combustion, so it is considered as a clean fuel. And it can be used in gas turbines and other combustion systems. However, hydrogen combustion still has a big problem. It can produce NOx in air, so even if hydrogen is carbon-free, it is not fully pollution-free. Also, hydrogen flames are different from traditional fuels. It burns faster, diffuse more easily, and are more unstable. Because of this, NOx formation in hydrogen combustion is completed, and you can see from the figure 1, it's hydrogen and hydrogen-based fuels is index increase in target net zero emissions scenario. So in this project, I compare my simulation results with the methods learned in the course, such as EDA, and analysis, and some random forest model, and begin from the next. I will give you two important conceptions, and the first one is mild combustion. This is a combustion mode with strong dilution and low oxygen concentration. It can help reduce temperature peaks and lower CO2 emissions in CH4 combustion. So there is an idea in hydrogen combustion if the mild combustion is fit for hydrogen combustion. And the definition of mild combustion is inlet air temperature bigger than oxygenation temperature bigger than temperature rise during combustion. And the next conception is about classical combustion. And you can see from the picture, the M1 is from the C1. It's after the combustion. It's a product from C1. And the C2 is from the inlet about the cold fresh combustion products. And they are indicated from the two rows. The C1 is the first stage combustor and the C3 is the second stage combustor. And as for the date 1 to turn is from the gas mixture. The after combustion products mix with the cold fresh combustion products. So you can think of it simply as follows. The higher of dilution K, the more mass of the thermal product Me is added to C2. And next, I will tell you one process is about analysis process. The first, we need to use Chemical and Katara to get our dates. And next, we will get to EDA analysis. I will plot box plot and residential comparison, mechanics selection, and third one is parameter influence. Analyze the influence of K on velocity, temperature, and NO and NOx. And last one is about modeling. For linear regression and random forest and poly 4. Yeah. And let's begin from the part 2. In part 2, I compare different mechanical mechanisms. Different mechanisms may give different results for temperature, velocity, and NOx. So before doing more analysis, I need to choose a suitable one. First, I use box plots to compare the distributions of 5 mechanisms. From these figures, I found that GDF K3 had a wide distribution, so its prediction changed a lot, and new 22-4 is more concentrated, but later I found its extinction position is too early, and for Joe 2023 has large dispersion for NO, so it is not very suitable for NO prediction, and for ELTE 2020 and Glarborg 2018 look more balanced. Yeah, and this for free flame combustion. And next, after that, I compare the solution results with experimental data. The date is from the paper, as you can see from here. And for temperature and actual velocity, Glarborg 2018 and Joe 2023 are closer to the experimental. GDK3 predicts higher velocity, and new 2024 shows early distinction. Then I check the NO resident shows. The result is for NO prediction only. GDK3 gives the smallest residential, but if I consider the overall performance, including flame behavior and profile shape, Glarborg 2018 is more suitable. So finally, I choose Glarborg 2018 as the main mechanism in this project. At the same time, I keep GDK3 as a reference for NO analysis. And let's get to the part 3. The influence of parameters K on flow temperature and NOx. As you can see from the part 3, which is a main physical analysis. In this part, I study how K affects velocity field, temperature field, and NOx emission. First, let me look at the velocity and temperature curves. These figures show that when K changes, both velocity and temperature also changes. For the velocity figure, the cases around K equals 0.3 to 0.5 or to 0.4 have higher peak velocity. This means stronger flow acceleration. For the temperature figure, low K cases show later ignition. So this tells us that K changes the combustion process early. Then I show the NOx emission index along the axial direction. From this figure, we can see that NOx generally increases with distance. This means NOx keeps forming during combustion. We can also see that higher K gives higher NOx values. When K keeps 2 equals to 1, NOx is the highest. Low K cases remain much lower. So the general trend is very clear. When K increase, the NOx also increase. After that, I showed the outlet results for NO, NO2, and total NOx. The figure shows that outlet NO increase with K and outlet NO2 is more in most cases, but is relatively high at low K, especially around K equals to the 0.1 and 0.2. Total NOx also increases with K. This means that the increase in total NOx mainly comes from the increase in NO, and I will tell you about the formula about calculation in NOx emission index. So from the part 3, we can say that K is a very important control parameter. It affects the inlet condition, combustion behavior, and final emissions. And let's get to the part 4, rapid prediction model for NOx. And why I want to build a fast model, and because detailed simulations in Katara or Kamikin are accurate, accurate, but they take a lot of time, and if I want to test many conditions, it is not efficient to run full simulations every time. So I want to build a simple model to predict all NOx emission index more quickly. And the basic idea is this: I use K as the main control variable, then I extract several important features from the simulation results, such as inlet temperature and oxygen more friction, peak temperature, peak velocity, and outlet's NOx emission index. Then I built 2 kinds of data sets. The first is the profile level data test, which describe the profile level data set, which describes the Excel profiles, and the second is the condition level dataset, which is used to predict the final outlet emission. An important point is that inlet temperature and oxygen concentration both change in K, and is linear regression. So in this project, K is still the main physical variable. Then I compare 3 models: linear regression and random forest, polynomial regression, random forest and linear regression. The results show that polynomial regression performs the best. Its error is smaller, and its R square is close to 1. That means the relation between K and outlet NOx emission is non-linear. A simple linear model is not enough. So the main conclusion of part 4 is a fast model can estimate outlet NOx without running a full simulation again. Also, median K values keep NOx relatively low, while high K values cause a strong increase in NOx. This model can be used for quick screening of combustion conditions. And the best condition level model is poly is the polynomial regression. It has more RMSE, MAE, and the R square is close to 1. Yeah. And finally, I want to make a short conclusion. This project combines combustion simulation with data analysis methods from COMP3115, and there are three main findings. First, after comparing several mechanisms, I choose this Glarborg 2018 as the main mechanism, and second, the dilution para K as it has a strong influence on velocity, temperature, and NOx. In general, higher K leads to higher NOx. Yeah. And third, I built a rapid prediction model for outlet NOx. This result showed that polynomial regression works better than linear regression and random forest for the dataset. Overall, this project shows that the data analysis methods from this course can be applied to a real combustion problem. And this work is all done by myself, so the code for the 1A1 and yeah, you can read the txt file in my source file. Yeah, and thanks for your listening. Yeah, thank you.